Let's assume that the location of the prelude in ULTRAKILL is physically inside the Earth. Using speedometers, it's possible to find the depth of the prelude using the acceleration due to gravity. But first, we need a relative length. Okay, so toilet paper rolls have an average length of 10 centimeters and are quite consistent in real life, so we can use that. Here's the problem. Aside from the massive uncertainty from such a small reading, it's not even accurate to begin with unless you're willing to believe that Gabriel is 120 centimeters tall. So instead we'll just be using the length of a barrel, which is assumed to have a height of 88 centimeters, which results in Gabriel being over 2 meters tall. Now that our speedometers actually have a purpose, let's assume that limbo and then other layers are non-physical. And we can start off by converting the U unit in ULTRAKILL into meters. V1 can travel through 65 squares in 3.65 seconds at a constant speed of 16.5 U's per second. A square is then deduced to be 29.33 centimeters in length. So that means 1 U is equal to 0.3245 meters. This means that the terminal velocity of V1 is 32.55 meters per second. And now since there is a terminal velocity, that means we should consider air resistance. The trouble with calculating air resistance is V1's mass is unknown. Although we can assume that a watermelon has the same terminal velocity as shown. Our next issue is density of air as it varies with temperature. Assuming that treachery contains ice and treachery's air resistance is identical to the prelude, we can simply assume that the density of air is 1.2754 kilograms per cubic meter. This is the density of air at 100 kilopascals and 0 degrees Celsius. We can easily calculate the surface area of the watermelon. Next, we need its mass. Assuming the probably mass of watermelon has an outer negligible thickness, assume the density of the entire watermelon is 0.64 grams per cubic centimeter. This results in a watermelon at a mass of 135.3 kilograms, which fortunately does not beat the world record, but it's still fucking massive. But next, we need to find the drag coefficient, which cannot be calculated easily. Using this image, I'll just assume that its drag coefficient is 1.38. Assuming weight and air resistance are the only two forces acting on the watermelon, we can solve this differential equation. Equate the constant of integration to be 0, since the initial velocity is 0. Get the function of time in terms of velocity by getting the inverse function, and then apply L'Hopital's rule to get the terminal velocity formula. Inserting all our values, we get a G value of 3.725 meters per second squared. Next, to determine the depth of L, we can use the law of gravitation. Because of shell theorem, we can assume that the upper shells of the Earth do not contribute to the gravitation at a given length. Using prem data for the Earth's density against depth, we can assume that the Earth continuously changes density with depth. Given that the volume of a thin shell is the product of thickness and surface area, we can use this integral to find the mass of a sphere with variable density. Dividing our G value by the gravitation constant, we need to get the ratio of sphere mass to radius squared, which equals the following number. We can deduce that the radius at which the Earth has a field strength of 3.725 newtons per meter is 1,021 kilometers. Which means if the mass is assumed to be perfectly flawless, humans have reached the inner core to reach hell, which in my opinion is quite a feat for the 22nd century. As for the flaws, watermelons, if not all props in general, start to accelerate a while after reaching the terminal velocity, which doesn't mean they reach a terminal velocity, they have a terminal velocity. But for simplicity's sake, let's assume they don't exceed their actual terminal velocity, since finding V1's mass instead would suck. Using barrels as a reference height would increase the height of toilet paper rolls to 17 centimeters. Not that big, but still quite big. Acceleration is actually a constant acceleration of about 12.6 meters per second squared. No value of density allows both to happen for our velocity time function, even if we consider the average acceleration before the terminal velocity is met. Using the param graph on Wikipedia, a pixel is about 10 kilometers, and finding the depth where acceleration is 3.725 meters per second squared is about 1031 kilometers.